Oh, that's yours. Okay, very good. So, can everybody hear me? How about the audio visual? Do you have? We're good? Oh, excellent, excellent. So before I get started, I want to take care of a couple of things that are of critical importance to at least a large fraction of the crowd here. As you may or may not know, this is actually I would call it a joint seminar, but kind of a joint seminar. It's certainly that Material Science and Engineering is the host department, but they were so gracious to add EECS as a co-contributor. And I think the grad students are going to be glad for that because in EECS we have compulsory attendance for seminars, and to make sure that you're duly recorded, we have a clipboard here. So I'm going to, there are I think 2 clipboards being circulated. One for,
we have the same rule.
Okay, so you got to check which clipboard you're looking for your name on because there'll be 2 of them coming around. So if at the end of this seminar I forget to pick it up, somebody make sure that either Steve Garverick or Chris Roberts is able to get it. Before I get started with the bulk of my talk, I just want to preface things by saying I'm a little bit under the weather. I have a little bit of bronchitis. I'm hoping my voice holds out, but we'll see how it goes. I've planned for a 3-hour seminar, but I'll keep it to 50 minutes. Not a problem. And as Art said, we're going to talk today about silicon carbide. And as you know, CASE has a long and rich history in silicon carbide research, and most of that has been directed towards harsh environment on the applied side, and then fundamentals of crystal structure on the fundamental side. And I want to take a little bit of a turn and show through the work that we've been doing in my group and through our collaborators that silicon carbide may in fact be a viable material for many biomedical microsystems. So before I get started, and because I can tend to be long-winded, I want to knock the acknowledgments out first. I have a number of collaborators whose work is highlighted in this talk, most notably Shuvo Roy and his group at the Cleveland Clinics, Gennady Shevitz and his group in the physics department at the University of Texas, and then Dustin Tyler and EBME. The students, of course, do all the heavy lifting in academic research, and my star students are listed here: Allison Hess, Rocco Paro, Zhang Gang Du, who's now a postdoc in the biology division at Caltech, and Jim Summers, who's working at a startup. I should point out that Rocco Paro will be joining ISIS on December 1st as a process engineer, and I think that speaks well for how we train our graduate students here at CASE, as they have told me so. Financial support for this work is derived from 4 principal sources: the Department of Veterans Affairs, where I also serve as a research scientist, NASA through NASA Glenn, CASE Alumni Association, and the National Science Foundation. So I'm going to presume that most in the room know something about silicon carbide, but we're on tape, so I think we ought to set the stage a little bit because there's a lot of acronyms and nomenclature that is in the vernacular of those who do research in silicon carbide. So silicon carbide is a polymorphic material, and I don't even remember how many polytypes have been identified, but there are 3 that are technologically relevant. 2 hexagonal polytypes denoted 4H and 6H, and the cubic polytype denoted 3C. And their crystal structure is illustrated in these cartoons here for the pleasure of the material science people in the crowd. Now, we have at CASE looked at silicon carbide for MEMS and NEMS applications for quite some time, and it's been targeted as a material for harsh environment applications due to some very outstanding material properties, like high sublimation temperature, large electronic band gap, high hardness and low wear characteristics, and its chemically inert properties. And of course, with this slate of properties, you can envision a wide range of MEMS structures and devices that can be used in environments where these properties would be important, like high temperature pressure transducers alongside high temperature electronics, valves, microbridges, flow sensors, and the like. The question is, however, especially on this campus, do harsh environments include those involved in biology? And I think the answer there is a resounding yes. It's not harsh in terms of temperature. 500C for biological systems, aside from maybe some that live around vents deep in the ocean, is too harsh. But chemistry provides a harsh environment where silicon carbide may have an opportunity. And it's, without question, CASE is a place where such research is actually very well suited, since we have a very strong and rich history in the biological sciences and biomedical engineering. So it seems to me to be a natural synergy between the two main efforts. Before we move on and talk about the real meat of the talk, I do want to talk a little bit about how one produces silicon carbide, because the production methods are peppered throughout the various projects that I'm featuring in today's talk. If you desire to produce single crystal material, you have a couple of routes. One, you can produce single crystal bulk substrates by a sublimation growth method. Save the details here, but suffice it to say that process requires extremely high temperatures, and at around 2000 C and above. If you desire thin films or even thick films, and you have a single crystal substrate on which you can grow those films, the temperatures aren't quite so extreme. Typical epitaxial growth processes are in the range of 1300 C for the cubic polytype and 17 to 1800 C for the hexagonal polytype. Many MEMS applications don't require a single crystal material at all and are well suited, are well adapted to use polycrystalline material, much in the same way that polysilicon MEMS is well adapted to many MEMS applications. Polycrystalline silicon is adapted to many MEMS applications. And one can deposit polycrystalline silicon carbide by LPCVD using a process that's much the same as polysilicon with temperatures.
Define the acronym.
Polysilicon.
No, LPCVD.
Thank you. LPCVD, low pressure chemical vapor deposition at temperatures a little higher than that used in polysilicon, around 800 to 1100 C. Amorphous material is also available for those who don't require a crystalline structure in their structural material, and one can deposit silicon carbide in an amorphous microstructure by a couple of processes, one being plasma-enhanced chemical vapor deposition and the other being sputtering, a physical vapor process. PECVD is typically performed at around temperatures of 300 to 500 C, whereas sputtering can be performed on substrates at temperatures as low as room temperature. I'm going to skip the popular applications because that's really preaching to the choir. It's all about high temperature stuff, and move right on to uses of silicon carbide in biomedical microdevices. I can't pretend to say that we're the first here to look at that. In fact, there are many groups out there today also looking at silicon carbide for such applications. And I point out two examples here just to show you the breadth of those. One example, the one on the left-hand side of the slide, is a example where the researchers at the University of Pittsburgh desire to make biofilters from porous silicon carbide. The starting substrate is a 6H substrate, commercially available, bulk wafer type, in which they engage in a reaction that forms a porous structure throughout the substrate, and the porous structure can therefore be used as a filter. And they were able to show that these structures were suitable in protein filtering applications. The other example, which is closer to some of the work I'm working on, is the use of a 6H silicon carbide substrate as a probe for neuro and other biological interfacing applications. And the the photograph shown here on the right-hand side of the slide is such an example. The silicon carbide probe is here. The rest is just packaging, most of it consisting of silicone, which is how a lot of our bio devices in early prototype stages are packaged. And they've showed that these structures can have some favorable performance characteristics when compared to the state-of-the-art in silicon probes, most notably with respect to mechanical properties and also some electrical properties. Amorphous silicon carbide has also been extensively explored for biomedical microdevice applications, and there are two groups that are leading the way here in the United States. One group is out of the University of Utah, led by Florian Sulzbacher, and he envisions using an amorphous silicon carbide thin film as a packaging material for micro devices largely built out of silicon. And he spent a lot of time investigating the hermetic behavior of these films. The test structures are microfabricated interdigitated electrode arrays like the one shown here, and he's also interested in making long-term implants, and so lots of experiments are conducted over long-term periods. In this particular example, the experimental trial ran for 185 days, and he's interested in looking at impedance changes as a function of exposure to biological fluids. A group out of Boston excuse me, has also been looking at silicon carbide protective coatings, and in their application they're interested in looking at the amorphous silicon carbide as a protective insulator for iridium wires that would be used for neural interfacing. So these are standard medical grade wires, and they showed that the silicon carbide coatings do perform quite well when used as a protective insulating coating for those wires, as shown in the data here in this graph. And then these photographs actually show that the silicon carbide coating can serve to protect the tips of these very finely machined wires from mechanical damage. This photograph here is of a silicon carbide coated iridium wire after machining the tip to a sharp point, and this is the same a similar wire but without a silicon carbide coating after machining, and their assertion is that the carbide coating lent mechanical stability to the wire and inhibited the deformation of the tip region here. So, excuse me, on to the work here we're doing at CASE. As I stated previously, a lot of my research is engaged in activities that's supported by the Department of Veterans Affairs, and one of the areas that we're interested in showing viability of microsystems is in the area of neurointerfacing. And CASE has a long and rich history in neurointerfacing through the Biomedical Engineering Department and the world-renowned FES Center. And the technologies shown on this graph here are illustrating some of their state-of-the-art approaches for neurointerfacing. And I won't go into the great details other than to show you that they have already implemented an implantable system that consists of neurointerfaces, a master control unit, communications for data and power that link the internally implanted devices to external controllers via a RF induction link out to a master control unit. And the photograph of one of the implantable structures is shown here. Neurointerfaces are at the ends of these long wires, and then the internal control unit is shown here. Along the same lines, colleagues in BME are developing advanced neurointerfaces that don't utilize the platinum wired construct that we would find at the end of the tip, but rather platinum foils connected to stainless steel medical grade wire and encased in a silicone housing as shown in these photographs here. And the platinum platinum foil interface allows for more contacts per unit area than the platinum tip. So with the idea that one would desire higher pixelation at a particular nerve site to get added functionality. Now, none of these structures are made using microfabrication techniques, and therein lies a limitation and an opportunity. The density of electrode arrays that one could produce in a structure like this is, of course, going to be limited by the manufacturing techniques that's used. And in this case, these foils are hand cut or machine cut, and the structures are hand assembled. So my colleagues in BME came to me a few years back and said, we desire to have a structure that would have a much higher density of contacts. Could we use microfabrication techniques? And I said, yeah, we could explore that. There are lots of challenges there. And so we're engaged in that activity. What we would ultimately like to see is taking a structure that's functioning now as this one and reduce it down to a more functional device at a localized level. And this is a cartoon that shows kind of a device structure that we would like to realize, where the nerve interface is on the back side of this wraparound structure. And on top sits electronics for data acquisition, recording, and stimulation, with some sort of connection to the outside world, either via a wired link, as shown here, or a wireless link. To realize this structure, we have to utilize, or we should utilize, microfabrication techniques, because these structures are envisioned to be non-invasive and located at places where a larger structure would be not practical. So how does one go about doing that? Well, we switch from, we believe the switch is, we need to switch from a polymer-based a silicon-based approach to a polymer-based approach. We believe that polymers will ultimately give us some of the attributes that are critically important, like mechanical flexibility, for the most part, as well as durability. There are issues, however, with respect to polymers, in that the polymers that would be used in these applications would require durability over extremely long periods, the target being 15 to 20 years if possible, which means that we require materials with extreme materials compatibility. The structures themselves aren't going to be of one material, but a multitude of materials. So there's challenges in material interfaces that need to be overcome. We've identified the body as a harsh environment, and it would be true that it would be harsh with respect to these devices. And in fact, the ultimate structures would be substrates or polymer structures where the properties could be either be tuned during synthesis or tuned after deployment to match the environment in which they're being deployed. The big one that we're targeting now is mechanical matching. So the first order approach is to look at what polymers are currently available on the commercial market and then try to reduce to form structures made from these polymers. So we've looked at liquid crystal polymer, polynorbornene, and polyimide as three candidates for the devices we're looking to make. Others would also be, for instance, parylene. We've discounted parylene because there's groups working around the country and making devices from parylene as a structural material. Liquid crystal polymer provides a decent slate of dielectric constant, mechanical properties, resistivity, and most importantly, moisture absorption. With polynorbornene, this is a commercially available polymer developed by a company in Brecksville, a close second. Polyimide is actually, there's a whole family of polyimides. This one may not be the best example to illustrate, but polyimides generally have a higher moisture absorption as a function of weight percent than the polynorbornenes and the liquid crystal polymers. Nevertheless, these moisture absorption rates are likely to be too high for a long-term implant anyhow, so we'll have to come up with a way to mitigate that. I'll skip that set of slides to show you the devices at some of the device structures that we've currently made. These are peripheral nerve interfaces here, designed to make intimate contact between platinum electrodes here and femoral nerves and other nerves located in the arms and legs. They're used and designed for acute applications, therefore the connection to the outside world is through a simple flex connector. A zoom in on the interface is shown here, and then this graph here shows one of the structures under duress during a deployment. And it's a surgical implant procedure, and you can see how contorted the structure gets. Nevertheless, these things survive, at least for short term. We have another set of polymers that are really early stage that are envisioned to address that issue of mechanical matching between the biosystem and the structure that's making the interface. And this is really a multi-investigator collaboration that includes biomedical engineering researchers Dustin Tyler, Christoph Vader, and Stuart Rowan over in macromolecular science, and then my group to do the micromachining and fabrication of the devices. And you've probably heard of this because it's been featured in several prominent journal articles as of late, Science and Nature Nanomaterials, as well as several press releases. So perhaps I don't need to go into the great details here other than to say that this polymer functions by actual moisture uptake. The polymer is, in our case, is PVAC, and it's laced with cellulose fibers extracted from a sea creature known as a tunicate, which is like a sea cucumber. and of course extracted in a disastrous way for that sea creature. Nevertheless, these fibers are imbibed into the matrix polymer, and when the matrix polymer when the polymer is dry in the dry state, the fibers are interlocking and form a matrix of themselves that make the polymer extremely stiff. When the polymer uptakes moisture, there's a change in the chemical interaction between the fibers, causing them to lose their interaction, and then the mechanical properties mimic that of the matrix polymer, which is extremely soft. And the macro group has shown that you can get a wide change in the mechanical modulus in these polymer systems. And then my group is looking to make a structure for neurointerfacing that looks somewhat like that. And we've actually made the base structures. This structure, if it's going to be electrically viable, is going to need films or some kind of a barrier between the sensitive electronic components and the backbone of the structure, which is this moisture-absorbing polymer. And we view that silicon carbide as one possible candidate. Now, for these applications, why silicon carbide? Clearly, it's not because of its high temperature capabilities. It's because it's chemically inert. We find that to be very attractive. Not only chemically inert for fluids in the body, but chemically inert with respect to chemicals we may have to use during processing of the device. We also like that it's mechanically durable. Why amorphous silicon carbide? Because that's our target area for this application. Amorphous silicon carbide is electrically insulating, unlike its crystalline counterparts, and we need the carbide film for its insulating characteristics. Also, it's an excellent diffusion barrier. It's been known for a long time to serve in that capacity. In fact, amorphous silicon carbide was used as an etch mask long before it was used in a micro device. And studies have shown that it's biocompatible. So those attributes are what's driving us. Why PECVD? Well, we actually have looked at both PECVD and PVD, but most of our effort up to this point has been with PVCVD because the deposition temperatures are within the range or close to the range that's determined by the polymers in which we want to integrate the material. So these are reasons for going after the PECVD approach. Now, we have two systems at our disposal, one located at NASA Glenn and the other one located in the microfabrication lab here at Case. And they're not duplicate systems. At the NASA Glenn Research Center, the system they have is a dual precursor system that uses methane and silane as the precursors. And we can deposit carbide films in a reasonable amount of time using the parameters shown here. Take note of the temperatures about 300 C. When we look at the mechanical stress, residual stress in these polymers, we find it to be egregiously high, minus 600 megapascals or 600 megapascals compressive, which is too high for our liking. We can relieve some of that stress by annealing the films, and the best annealing conditions we found to date is around 450 C, and we can actually convert the stresses to tensile by annealing at that temperature for somewhere in excess of about 10 minutes. So we can produce a film that has stress-relaxed characteristics with a short-term anneal, although I would say that annealing temperature is a bit high for my liking. These are with respect to silicon substrates. We are also not only interested in the stress, but we are interested in other mechanical properties for bio and non-bio applications. And in my group, one means by which we extract the effective Young's modulus is by way of using micromachined devices, most notably bulk micromachined membranes. And we find silicon carbide to be one of the easiest materials to bulk micromachine when it sits on a silicon substrate because it's completely inert to the etchants you would use to remove the silicon selectively. And the fab cross-section is shown here. Perhaps most of you are familiar with this simple bulk micromachining process. Membranes are easy to make. Here's a picture of a chip with a thin, about 1/2 micron thick silicon carbide membrane suspended across a gap that ranges somewhere between 300 microns and about 700 microns, I believe. That's the typical 750 by 750 is our typical test specimen. What we do with these membranes is we load them with pressure, and we look at the load deflection behavior, and from that we are able to extract the residual stress and the effective modulus. And in my lab, we have an instrument that makes this measurement relatively easy to perform. We have an interferometer that's mounted to a microscope. The chip is mounted to a chuck that's attached to a pressure manifold. We load the membrane with pressure. Pressure's up in excess of 50 degrees, 50 psi, and then we look at the interference pattern on the loaded membrane, and then we extract the deflection data from the depressurized membrane as we get it from the interference rings. So the measurement technique is to load up the membrane, then slowly release the pressure, and look at the deflection profile as the pressure is dropped. We then take the data that's collected and we map it against this well-known equation that has a number of important parameters, geometric parameters here and here. We have the effective Young's modulus in the cubic term, and we have the residual stress in the linear term. There's two distinct regimes in this data, one where the Young's modulus takes primacy and the other where the residual stress takes primacy. And typical load deflection data is shown here. We find these techniques, this particular technique, well suited for lots of statistical analysis because you can generate large sums of data, and we can extract the average Young's modulus. And in this case, we find it to be 133 plus or minus 6 gigapascals with a residual stress where we thought it would be based on our annealing conditions. Those who know the Young's modulus of single crystalline and polycrystalline silicon carbide will note that this is considerably lower than you would get from those films. And we think that's actually a positive attribute for the applications we envision, because we want to interface it with polymers who can actually have a modulus that may be a couple orders of magnitude lower than this. So we're not trying to exploit high modulus in this case. If we find it interesting, if you deposit the same film on a silicon dioxide substrate, which is amorphous as opposed to single crystalline, the residual stress is relatively insensitive. At least we can't say that it's statistically different, but the Young's modulus is a bit lower. And I suspect that there's a relationship between the starting substrate and the resulting material, although more investigation is needed here. At present, we're still driving this from a technological perspective, but we'll likely go back and take a look at this once we find that. Sure.
One more.
So the bottom line here is that we're interested in the interaction between the film and the substrate. We've explored 2 substrate materials using this method, and we'll move to other substrate materials as we're able to do so, perhaps polymer substrates, to see if the modulus is yet affected. Another area that we're interested in switching away from the mechanical aspects of silicon carbide is to see if it would be suitable as a thin film packaging material for wireless microsystems. You envision the ideal thin film, ideal packaging material is one that has a very low footprint, as if it's not even there. So the device carries most of the volume. In reality today, most implantable devices, most of the volume is with the package and not the device. Ultimately, we like to turn that around. So we would like to come up with thin films as packages. For this to work, we need the thin film to not impede communications if we're going to use a wireless link. And so we suspected that because of silicon carbide's insulating properties, it actually might work well as a packaging material or a protective coating for wireless microsystems. So I actually had the pleasure of spending a couple summers at NASA Glenn as a summer faculty fellow in the communications group, and they have all this wireless microsystems testing capability, and I convinced them that it might be interesting to just coat some of their already fabricated antennas with carbide and then let's do some tests. And maybe they just said, we got to keep Zorman busy, so let's let him do that. But nevertheless, we did. So we picked one of their standard antenna structures. It's a coplanar waveguide structure. The details are shown here. Most important for those who are EEs is that it's designed to operate at 2 frequencies, 5 gigahertz and 7 gigahertz. The structure is relatively simple to render. It's just a patterned metal structure on an insulating substrate. We didn't go right to the polymer substrates, as you might imagine, for a making implant devices, because in fact NASA wasn't in the business of making implant devices. Instead, they had readily available these antennas fabricated on alumina substrates. So the conductor's made of gold, alumina substrate. This is an uncoated antenna, and this is one coated with silicon carbide. The connector area here was left uncoated because we worried that there actually might be delamination over those large features. So then we did a simple battery of tests. One was to look at the return loss, and the other one was to look at radiation patterns. This is kind of the standard in testing that they do when they come up with a new geometric design. And I'll jump right to the return loss data. This plot here shows return loss, S11 parameters, for uncoated and silicon carbide coated antennas. And as you can see, or maybe you can't see if you're in the back, it's really hard to distinguish the pattern between the two. It's relatively indistinguishable. If we zoom in here, you can see small differences, but for the most part, they would be of really no great concern to implementation of this device. We can look at the radiation patterns, and over at NASA Glenn, you can look at E fields and B fields, and you can look at them in a variety of dimensions. Here we show the E copole and H copole patterns for 5 gigahertz with and without the silicon carbide film. So there's 2 data sets superposed on that graph and 2 here. And you can see it's really hard to distinguish the 2 antennas here. It's a little easier to see a difference here, although the pattern is the same. And I was told by my colleagues that the difference here is mostly due to experimental setup. Alignment's critical in this, and if there's a slight misalignment, you'll get a little bit of difference. But what we were looking for is great pattern changes, which would show that the antenna was affected. We can also do that for the 7 gigahertz antenna, and we see, again, the trend holds true. Bottom line is the assessment. Oh, and then we took these antennas that were coated with carbide and we stuck them in a gold etchant. We're like, well, it's not good as a packaging material if it doesn't protect the metal that it's sitting on top of. So we stuck it in there for 24 hours, and we saw no degradation in the coating and no loss of the gold that sits underneath it. So that simple test suggests to us that we have a thin film technology that, at the very least, is suitable to protect antennas from harsh chemical environments and motivates the work to move towards a wireless implantable microsystem. That is, if we can get the silicon carbide film to behave well on a polymeric substrate. So then after coming back from the second summer there, I went, or actually it was the first summer, I went to my colleagues in the BME department who were having me help them make these microfabricated interfaces, and I said, would it be interesting to take a look at how carbide films would go down on them? And they said, absolutely, let's take a look at it. So we came up with an interface design that would be convenient to examine from the perspective of the fabrication issues, as well as perhaps convenient to use in acute testing. As it turns out, it's not a very convenient architecture for acute testing. We've come up with better ones, but from a fabrication perspective, it works very well. The fabrication process, in this particular case, we elected to go with Polyimide because it was readily available, and the work at the crowd up in Boston suggested that we would find some success because that's what they had been looking at. So the process is relatively straightforward. Those who are familiar with silicon processing would recognize this as the typical monolithic processing sequence, with the exception that instead of using the silicon substrate to support the entire structure, we're only using it to carry the substrate, which is a polyimide sheet. So we stick the polyimide sheet to the wafer, we put on our metal electrodes, and then we put on a silicon carbide capping layer, and then we are actually able to show that we could use, in amorphous case, photoresist as an etch mask for plasma etching. And that's in contrast to the crystalline forms, which usually require a metal etch mask because they're much more chemically durable and mechanically tough. So photoresist is usually out. We're able to pattern vias into the carbide film right nicely using a photoresist etch mask, and then you finish the process by putting down an etch mask for the polyimide, which in this particular case required metal because it was thick, and we couldn't use a photoresist, so we deposit and pattern an aluminum etch mask, and then we etch the polyimide structures using that a separate RIE process, and then we demount the structure from the silicon carrier wafer. The etching conditions are shown here. For time, I won't go through the details, other than to say that we found that we could perform a silicon carbide etch that was highly selective to both the underlying polyimide as well as the overlying photoresist, meaning that we could expose our metal structures underneath without risk of etching into the substrate, and we could do the exposure while maintaining pretty good fidelity with the overlying polymer etch mask. And here are structures, typical structures here. The iridescent cast that comes off of these structures is the silicon carbide film. You can see it here and here. So at first pass, it looks like a pretty good process. Should be a good electrical insulator, overcoats the metal. In fact, if you zoom in on the metal structures, you can see this is exposed metal. This is silicon carbide sitting along the edge as designed, and then this is carbide-coated polyimide on both ends of the structure. The pitting here is because the polyimide sheet was actually not all that smooth because it's just commercially available stuff. However, we found that although it looked good at first, if we were to expose this carbide film to aqueous solutions, bad things began to happen, which means we haven't solved all the problems yet, but we can see some of the really bad things here. There's debris, it looks like debris in here. If we zoom in here, we find striations in the film, definitely catastrophic cracking. And we're asking ourselves whether this cracking is related to stress, and most likely, yes, it is, because we didn't have a mechanism at our disposal to relieve that stress other than annealing at perhaps 450 C. And those who know polyimide know that 450 C is at the upper bound of where you'd want to take that. Likely it would be stuck to your holder when you pulled it out of the annealing furnace. So we've got stress-related issues to deal with. Not certain at this point whether changing the recipe will reveal a lower stress film out the gate, or we're going to have to come up with another mechanism. But lacking any real insight and guidance here at this point, I just said let's switch to another deposition mechanism, at least to explore it. NASA Glenn has a sputtering system which is available to us, and we convinced them that we should try to explore sputtered silicon carbide, and this data actually came to me earlier today. So I have had enough time to digest the essence of this graph, but I can't say much more about the films other than to note the following. This is stress versus annealing time for 3 annealing temperatures, 450 C, which is our benchmark, and then of course we don't like that annealing temperature, so we explored in this experiment decreasing annealing temperatures. And you can see that as deposited films have extremely high compressive stresses that can be changed to tensile stresses after a short anneal. This is much the same behavior that we see in the PECVD films. But in this particular case, I should mention the PECVD films, when we would anneal at lower temperatures, we didn't see much of a difference in the residual stress. But here you can see that at 250 C, the overall tensile residual stress is about a factor of 2 lower than at 450 C. And at 250 C, if we're willing to sit for 30 minutes, we can actually get a film that appears to have very low stress. Now, I don't have error bars on here, so I don't know exactly where that line sits with respect to, near zero. So it could be on either side. But nevertheless, I think the trend will hold up as we look at this data from a statistical manner. And 250 C is well within the range of temperature tolerance for a number of the polymers we're interested in, most notably liquid crystal polymer. So we're ready and staged to go and take a look at that as a possibility. Now, I haven't mentioned anything about the amorphous silicon carbide films here at CWRU, and I'm ready to do that now. The application space for those particular films at present is not on polymeric substrates, but rather as a non-biofouling surface. And so the silicon carbide the system here is not equipped with a dual precursor capability, but rather we use a single precursor, trimethylsilane. It's commonly used in IC, well, it was developed, I shouldn't say commonly used, it was developed for IC fabrication when there was a big push to insert copper metallization in the back end of transistor fab. The rationale being that copper needs to be isolated from the underlying transistor, which would require an excellent diffusion barrier material. And the thinking was that silicon carbide would be that. But not only does that film have to have excellent diffusion barrier characteristics, it has to have outstanding dielectric characteristics, and I think the verdict is still out there. I haven't really kept up with that line of research, but I knew that there was a large body of research out there that could guide us in developing suitable deposition processes, so we went ahead and did it. We did note that no one had at this point used that precursor to fabricate MEMS devices, so that was an additional motivation. So of course we're going to track stress as a function of annealing temperature. As deposited stresses in this particular class of films is much lower than the dual precursor. Yeah, it's around 100 to 150 megapascals compressive, so it's better than before, and it may be acceptable in some cases. That film can be converted to a tensile stressed film by annealing at 450 C for around the same amount of time as you would the dual precursor films. We were interested in the surface characteristics of this film, and so we actually started working with, I think, Clements Berta's group to do some FTIR. This was work done by John Dew, who's now at Caltech, and he was interested in looking at the signature from an as-deposited film and a film that was annealed under conditions that would give us stress levels suitable for bulk micromachining, around 100 megapascals tensile. So you can see the data shown here. In the unannealed samples, we find that there are signature peaks here around the SiC, which would be indicative of silicon carbide, and that there also is signature peaks coming from hydrogenated carbon and hydrogenated silicon, which isn't of any surprise because that trimethylsilane carries with it quite a bit of hydrogen. When you anneal the films, you can see that the signature for the silicon-carbon bond goes way up, and the signatures for, I can't explain that one there at present, but some of the other signatures are either not modified much or only modified slightly. We then went back to the material science department and said, well, I had some experience in my dissertation days with RBS and ERD, and I said, okay, I can understand that data much better. So we went back with the same films and looked at RBS and ERD data from unannealed and annealed films, and we find from the ERD data that the films lose about 50% of their hydrogen after annealing, which I didn't find to be all that surprising, but it may suggest the relationship between chemical composition and stresses in the film. We're looking at that in more detail. We could micromachine membranes from these films, and we did so, and we used our load deflection testing, and we found, again, a typical load deflection behavior. And we found in this particular case that the films had a Young's modulus, or an effective Young's modulus, is even lower than before, around 75 gigapascals. For reference, this is one for 3C, a film, a 3C, single crystal 3C film measured using the same technique. So it's even lower. I think that's actually a good thing if we're going to interface it with freestanding polymeric substrates, but again, we haven't gotten quite there yet. And actually, it begs the question, will these properties translate to non-silicon substrates, most notably polymers? We did find, however, since we could modulate the stress quite nicely, and we knew that hydrogen effusion was likely the mechanism, we thought, well, let's look and see how we could use this film in a host of micromachining applications. And one we were particularly interested in is bonding, because in many bio applications, especially those that are directed towards microfluidics, bonding of two separate micromachine substrates is often critical in realizing the final device. In crystalline and polycrystalline silicon carbide, bonding is not possible without help from an adhesion layer like an oxide film. It's very difficult to activate that surface to get a direct bond. And even if you can, the surfaces are usually too rough, or the stresses are too high, and either the substrate bows or they can't get intimate contact to get the two surfaces to fuse together. But we know that from our previous work that silicon carbide in the amorphous phase got a lot of hydrogen in it, and that surface is likely to be more chemically active in ways that would facilitate fusion bonding. So we went about taking our inspiration from the silicon world that suggests that silicon bonding is enhanced if you treat the surface with an oxygen plasma, and we basically mimic the same process. We exposed an amorphous silicon carbide surface to a plasma, 150 watts, oxygen plasma, modest amount of time, and then we took the two surfaces right after plasma treat, we went to a vacuum bonder, and we were able to join the surfaces together. And at a temperature of only 150 degrees C, we could fuse the two surfaces together and form an intimate contact that not only joined the surfaces together, but formed, at least short-term, a vacuum seal. And what I mean by short-term is we haven't tested it for years, but that is shown here in this photograph where we have a suspended membrane that is spanning a micromachined circle that is in the underlying substrate. And the rings here are diffraction rings that come about by that membrane deflecting into the cavity by virtue of atmospheric pressure pushing against it. And if there was atmosphere on both sides by way of a leak, you'd see a flat membrane. I have other pictures that show what happens if you don't get the proper stress and the things look ugly, but they still join. So we've got a vacuum sealing process. Along the same lines, we're interested in looking at not only activating the surfaces for joining and forming silicon carbide structures, but also for creating surfaces that are bioinactive with respect to fouling. I have a project at the Cleveland Clinic to look at nanoporous micromachined silicon membranes for biofiltration applications, and you may be familiar with this work. We use micromachining techniques with a twist that capitalizes on the well-understood oxidation behavior of silicon to form pores that consist of nanoscale slits that separate two polysilicon films. If you're interested in the process details, I'd be glad to talk to you at any time. You know where you can find me. Typical pore sizes range from 5 to 100 nanometers. And in our vernacular, we use pore height to describe pore width because we're trying to kind of match up with the filtration community here. What's the motivation? Well, we would like to build artificial organs that are manufactured and not grown genetically, and two in particular of interest, one a kidney and a pancreas. And the motivation behind making an artificial kidney is as a way to deal with the increasing problems associated with diabetes in the United States. Nobody really desires to go to dialysis centers, and if you can miniaturize a bunch of that, make it wearable, then you have a viable technology that improves human conditions. A viable filter, however, has to have mechanical durability as well as biodurability. And one thing that will happen to filters is that they will, if they're effective, block the unwanted stuff, and if they're really effective, block a lot of it, all of it. But in the process, they may become fouled. And when they become fouled, they become blocked. And when they're blocked, they're not effective. The system would shut down. We would desire, and we can construct a architecture, fluidic architecture, that would keep the surfaces clean through transflow across the surfaces if what's being filtered out won't stick to it. So this is an example of a silicon structure, and you can see that there is junk sitting on its surface, and that's biomaterial junk that's adhered to the surface. The filter works well, but it begins to foul. So we wanted to engage in fouling, anti-fouling studies or fouling studies. So we looked at exposing silicon carbide surfaces. This is amorphous silicon carbide to a fairly standard mix of bioactivity stuff. And I'm looking at the clock, and I know I've got to watch my time. So suffice it to say, we followed standard protocols at looking at fouling. We looked at surfaces, silicon carbide, silicon dioxide, and then a control that were native or nude, and those that were coated with what's called PEG, polyethylene glycol. It's known to be a surface coating, a surface monolayer coating used to suppress fouling. And the polymer structure is shown here, and the evidence that we actually successfully PEG-coated the surfaces is shown here. And this is from a silicon carbide sample, and what we're really looking for is carbon-carbon and carbon-oxygen bonds. We can't completely mask the carbon-silicon bonds because they're going to come on the substrate. this is the real important data here. We conducted studies that looked at uncoated and coated samples. You can see the battery here, exposed to the media over a 12-day period. And all these other ones show, as the light blue indicates, cell attachment. In this case of silicon carbide, the uncoated samples showed, in some cases, very little cell attachment. In other cases, there's some. But in contrast to all but the oxide, it's a marked difference in the uncoated. When we look at peg-coated, you can see there's a huge difference between the attachment on all other silicon derivative surfaces and that with the silicon carbide. It made us wonder what was going on there. We still don't have a viable, robust explanation for this difference, but we've looked at it from a technological perspective, and we looked at the durability. Perhaps it's the durability of the peg coating on that silicon carbide surface. So we looked at the durability of the peg coating by measuring contact angle under air conditions for a 20-week period. And this was actually experiments done by a student intern over at the Cleveland Clinic. And she did an outstanding job and presented this at a conference last fall. You can see that the contact angle remained relatively stable over the entire period, except for a little bit of a drop at the very beginning. We looked at contact angle under physiological conditions, and that would be under PBS solutions under these temperature and gaseous conditions. And we see that it remained relatively stable for a 60-day period. And we looked at protein adsorption under the conditions shown here for, I believe, a 60-day period. And we compared that to an uncoated silicon carbide sample. These are peg-coated ones. And then this is the control specimen, which I think is a polycarbonate. And you can see that the peg coating under physiological conditions with respect to protein absorption remains stable as well. It's very low and remains stable, especially compared to the control specimen. So we believe that there's a real opportunity here for using the amorphous silicon carbide as a non-fouling material. Now, last topic, if you'll bear with me, I have to talk about it because it was in the abstract. I have switched gears from the amorphous silicon carbide and moved back to the single crystal silicon carbide. That's where I got my start in the field back in 1994, and fortunately it's come back to bless me in ways that I could never anticipate. A colleague of mine at the University of Texas is a physicist, and he called me one day and said he's been doing calculations, and he knows from his calculations that silicon carbide has a negative, maybe I should jump over to here, a negative permittivity at around 11 microns wavelength. And it's a positive permittivity on all other wavelengths that he probed. He said with that attribute, you have a material that for a small range of irradiation will behave like a negative index material. Now, many of you may have heard of this negative index phenomenon. It's all the rage in making cloaking devices, cloaking wear and stuff, where in a negative index material, light behaves with a left-handed rule as opposed to a right-handed rule. So when you look at light passing through a material that behaves under normal conditions, right-handed rule, you get this deflection. Here's your light source and it spreads out. A left-handed material, however, will behave in such a way that an image here will be focused on the other side of the material. The physics takes about 20 minutes to talk about, and I'm sure you don't want to spend another 20 minutes going on about it, so we'll just have to say, suffice it to say, that's what happens. He and I got together, and he postulated that we could build from a silicon carbide film a structure known as a superlens. And a superlens consists of a material that exhibits this negative permittivity under the irradiation conditions, clad by another material that has the same permittivity but of opposite sign. And as it turns out, silicon dioxide at 11 microns has in absolute value the same permittivity but opposite sign to silicon carbide. If you can create this cladded structure and you illuminate it with the proper radiation at the proper wavelength, you'll excite evanescent waves that are constrained to move along the interface of the material. Those waves can be probed using a a technique known as, oh, do I have it? Where did it go? Near field scanning optical microscopy. And in essence, what that is a customized AFM that probes the surface of the substrate for these evanescent waves. So you image the signature of the substrate not by a mechanical deflection, but by the evanescent wave signature that you get from that probe. So the attribute here that one was trying to capitalize on is that these NSOM devices actually cheat nature by having a resolution that's well below the far field diffraction limit. Typically speaking, your microscope's resolution will be limited to about λ/2 because the microscopes work in the far field and diffraction ultimately takes hold. So information is lost. But if your probe, that gathering the signature coming from the sample, can be put very close to the surface, like that in an AFM, one can capture that data back, and it's been demonstrated in a number of systems that the resolution then is improved to λ/20. But you got to get the probe really close to the surface. So that makes this scanning microscopy an attractive tool to study biological systems because now you're no longer diffraction limited. So you have this really high resolution, but the problem is that you have to get your probe really close to the specimen. And for non-biological systems, that's okay, but for biological systems, the best data is going to come from a biological specimen that's kind of in situ, in solution at least, so it's live and living. The standard techniques will be very hard to implement in that way. So my colleague said, we'll build the super lens. And the super lens will extend the depth of field of the NSOM to a point where we can then use it to image biological systems in their environment. How are we going to build the super lens? Well, we'll use Case's trademark film, which is this epitaxial 3C. The recipe hasn't changed since 1995, although the applications keep getting broader. Makes a very good film. We're going to construct the super lens from the silicon carbide film. In this case, it's submicron, 440 nanometers, clad with 220 nanometers of PECVD deposited silicon dioxide. In this particular experiment, we're going to image a gold film that has a pattern registered on its backside. We're going to put the gold film right on the backside of the super lens. So the super lens is this area in red here. Our probe comes in from the top, the NSOM probe, and our 11 micron radiation comes in. By the way, that's generated by a CO2 laser, which isn't all that hard to get. If all things work out right, we will, using this probe, get a signature of some sort from the image of this patterned gold structure on the backside. But it only will work if we're at resonance. That is, if we're close enough to where superlensing takes place, around 11 microns. If you're off 11 microns, it falls off. The patterns that we were imaging in this case are 540 nanometers, 860, and 1200 nanometers. And if you do the math, this is λ/20. That's the λ/20 criterion. So here's the data. This was published by my colleagues in Science a couple of years back. Here is an SEM of the image, the patterned gold film sitting on the backside. These are images that are acquired from this tip as it sees data coming from the super lens, not from anything else. You can see here, this is at resonance, 10.85 microns to be precise. It's easy to resolve those larger structures. You can resolve these, and then with a slight tip of the head, you can see that there is a fairly close facsimile to the structures over here. And I'd have to do some image processing to pull those out, but there's a bit there. If you go slightly off resonance, in other words, you tune the laser to 9.25 microns, the image completely disappears. This is imaging coming from the evanescent wave signature that the super lens is able to pick up. In other words, excitations, electromagnetic excitations along that interface that are lost by other optical means. The significance, we don't have time to go over this data, but it shows again that When you're on resonance, you get a very sharp peak, and when you're off resonance, most information is lost. And when you're close to the excitation wavelength, you actually can pick up other modes, and when you're off, they completely disappear. Why do we find this an exciting opportunity for imaging? Well, silicon carbide, and this will be my closing slide, is inherently micromachinable, as we know from our experiences here at Case. You can make it non-fouling. It's probably non-fouling anyway. It's mechanically robust, even in thin film membrane form. It's chemically inert, and it's highly micromachinable. If we were to build a simple we are actually building a simple microfluidic system that consists of a substrate that has machined into it somehow or printed into it somehow fluidic channels that will serve to deliver biological specimens. We claim that we would be able to position the biological specimens within close proximity to the NSOM tip and would be able to utilize that lambda over 20 capability that is inherently exists with the NSOM structure to image the biological specimen in its natural state, because the super lens allows you to extend the depth of field. Our simple non-bio experiment showed that it could extend the depth of field by 880 nanometers, and that we can build the lens quite easily doing that. And if we make this fluidic channel relatively small but still fluidic, we believe we can do imaging there. And it could open a host of new studies that can be conducted using this microscopy technique. This is a relatively new start. We received the NSF NERT last year. I'll be reporting on the latest findings in a meeting in DC next week, and it'll be ongoing for the next 3 years. So in closing, I'd like to thank you for your attention. I hope that you get the impression that we've got a lot of opportunities here in all flavors of silicon carbide to do bio research. I know I probably chewed up all my question and answer time, but I'm a local guy. You can find me at any time in my office, and next semester I'll be lecturing in here 9:30 to 10:20, Monday, Wednesday, and Friday. And before I turn it back over to Art, if you are excited about these technologies, you may consider enrolling in EECS 434, Intro to MEMS, to be taught Tuesday and Thursday from 2-something to 4-something in a location to be determined. And I'll be teaching that class. And with that, have a happy Thanksgiving and be safe.
Well, we're not going to let you get away with that question. So, Steve.
Have you ever deposited the silicon carbide coatings, thin films, onto active circuits?
We have not. We have not been, it's not that we haven't been brave enough to do it. We wouldn't know an active circuit if we saw it. No, not. We would need somebody to provide us an active circuit that's properly characterized prior to deposition, and then we could look at it again. And my group isn't well equipped to do that kind of a test, but perhaps we can work with your group and take a look at that. But we haven't done that yet.
What temperature are you using for the deposition?
Well, the NASA system's at 300C, the Case system's at 350, but we haven't tried to push the Case system down to lower temperatures because we kind of locked in on the non-fouling properties. And the sputtered system deposits at room temperature. And if you have to mitigate stress, it looks like 250C will get most of the stress out. It's not so much the deposition temperature, it's whether you can tolerate the stresses in the as-deposited films, or do you need to have those taken out. And to do so, then your thermal budget is driven by the annealing curves that we have.
When you showed residual stresses, what were the substrates for your films?
Okay, so in all cases where I guess I could say, in all cases the substrate was silicon. The data that shows stress as a function of temperature is extracted from a simple wafer curvature measurement technique, and then we would micromachine the structure to look at local stress using the membranes.
I would expect that the residual stresses are going to be completely different on polymers. Is that a right guess?
Yeah, I think you're out. I have no intuition as to whether it's going to be better or worse, but it's going to be different, to be sure. Yes.
Okay. And can you just tell me, because I don't know what the origin of the thermal stresses is, or stresses, is it all thermal, or is it?
I think, okay, so in in the crystalline materials, I think there's two components that will govern most the stress. You're going to have the structure, and so you're going to have a microstructure related stress because you've got crystals, and you may have an epitaxial relationship and a mismatch, and then you're processing at these high temperatures, so a lot of it's thermal. You're going to grow at 800 to 1300 C and cool down to room temperature, so a lot of it's thermal. There's about an 8% difference in the coefficients of thermal expansion, so it's going to build in stress. It's going to be hard to get out by other means. In the amorphous case, we're most of the time not even dealing with a pure silicon carbide. It's going to be containing some hydrogen in the PECVD cases. In the sputtered cases, I don't know where hydrogen would come in, so it's probably either stoichiometrically not balanced, but it's still silicon and carbon. There, I don't have a good feel right now as to which mechanism is dominating, but I know one thing. I believe when we heat the sample up, we change it. So, and in changing its structure somehow, chemical composition, maybe its actual bonding structure, the stresses change.
We've studied residual stresses in silicon deposition at great length, so there are intrinsic stresses which, as far as I know, must be due to interstitials of some sort, because they're almost always compressive.
So I actually threw that and highlighted some of the mechanical stuff in here because I knew that we have experts around who, if they're interested in this line of work, there would be fruitful collaborations possible.
And I don't believe two of your data.
Okay.
I don't believe that the modulus of silicon carbide deposited under the same conditions on SiO2 or some other substrate can be different.
I wouldn't argue strongly for that to be the case, but I don't have we do the measurement, and at least with respect to the measurement. Now, there may be an issue with the measurement itself, but the way we perform the measurement allows us to get statistically identifiable data.
We've done membrane curvature, and I still don't believe that these thin films have a modulus that depends on the substrate.
I'm not surprised.
Any other questions? Well, I've got one. Oh, go ahead.
What kind of film silicon carbide?
Here, on this particular one, this would be a 3C film grown on a silicon substrate. And it would be, we call it an epitaxial film. It's a heteroepitaxially grown film. It's single crystal for the most part, with lots of defects in it.
So does that require typical special thickness or
That's a good question, and that's actually one of the things we're looking at in this NERT program. The thickness is selected here mostly governed by two factors. We need to make sure that we can get an optical signature through the film, because we have to interrogate the sample, so we don't want it to be too thick. We don't want losses to dominate. The evanescent waves are pinned very close to the surface anyway, and we don't want to lose them through the bulk. That's more important for the cladding layers. But we need the film to be strong enough to be mechanically durable and will actually sit as a capping layer on top of the microfluidic channel. So other candidate materials might not work very well because it's difficult to render a thin film membrane from them. So we're fortunate that the optical properties and the mechanical properties are kind of coincident enough to at least allow us to build some prototype structures.
Well, Professor Peruse is another silicon carbide expert who I've known for many years. I've never heard him talk about phonon polaritons. Could you please elucidate what those excitations are? I don't think I could if I were asked.
Well, that's, I thought about just leaving that out and just punting and saying I'm a converted EE and all that stuff. Sounds really good. I'll do my best. Are we on tape? Can we go off tape now?